Hello, my dear students. Welcome to BYJU'S exam prep. In this particular ground zero video, today we'll be talking about a very interesting and important topic, that is condition of tipping. Why I'm saying this is important, because many students have a confusion, sir, when the body will be undergoing a sliding motion and when a body will be undergoing a tipping motion. Tipping means the body is tilting about one of the ends, right? So it's very important you should be knowing the detailed discussion of this particular topic. And also there are some slight confusion that will be clarified if you watch all this particular video till the end. Okay, so let's start the discussion so that we are able to have more clarity about what is the condition for tipping, right? So let us suppose I'm having a body and it is kept on a flat horizontal surface, right? So definitely if I'm not applying any force, so if I say this as an example, if I say this is the body I'm keeping on a horizontal surface, then what will happen? This body will be in static equilibrium, right? This body will be in static equilibrium. Okay, so if I try to write the condition of this body will be having a static equilibrium, right? And if I try to do the FBD, will be having a force acting, the weight acting downward, okay, passing through the center of gravity, that is point G, right? And we'll be having some normal reaction. Like in this last discussion, we have already seen that friction is basically happening due to multiple causes. Like we are having a rough surface, we are having a chemical bonding, due to there is a multiple point contacts, and due to multiple point contacts, what will happen? We'll be having normal reaction at each and every point. So in totality, if I say there are like many point contacts, they will be having some normal reaction like this, right? So these are the multiple normal reaction at the multiple point contacts. If I try to add all the summation effect, it must be passing through the center of gravity. This N is nothing but the normal reaction, and this is nothing but the algebraic sum of all the force, and it has to pass from the center of gravity. Because if it is not passing from the center of gravity, then what will happen? We'll be having a couple being created, right? So this body, as this is static equilibrium, that means the total summation of force and the total moment should be equal to 0. Okay, that is the basic understanding of equilibrium condition. Sir, very easy. There is nothing new that we are talking about. Let us suppose I'm having a block, right? I'm having a block. Now I'm applying a force P on this block. Okay, fine. I'm applying a force P on this block. So if I try to apply force P on this block, then what will happen? If I try, and this force P, this P is the applied force. P is nothing but the applied force that we are applying. Okay, such that this applied force is less than the limiting friction. That means if I say this is that body, I'm applying a force on this particular body, but this force is less than its limiting force. That means this force is not sufficient enough to move this body. That means, can we say this entire body will be still in a static equilibrium? Yes, this body will still be in a static equilibrium. Why? Because this body is at rest only. If I'm applying a force P, again I'm applying a force F, because this force P is not sufficient enough to overcome that limiting friction, right? So can we say this body is in static equilibrium, right? So if I try to draw the FBD, now normally if I try to draw the FBD, what will be having? Sir, we'll be having one this is the center of gravity, this will be the weight of the body, okay, right? And if I try to draw the normal reaction, this will be the normal reaction, and this will be the direction of friction. Okay, right? The body is in static equilibrium because you are applying a force less than that of limiting force, okay, limiting friction. Now you will be saying, sir, total horizontal force is equal to 0, P equal to F. No problem with that. So total vertical force equal to 0, normal reaction and weight is equal to 0. That is W is equal to 1. Sir, are we having a moment equal to 0? If I try to calculate the total moment about point G, W, P and N is creating a 0 moment. But what about this F? This F is creating a movement in the clockwise direction. That means this movement about point G is not 0. Are you able to visualize the concept that you might have studied, that always it is passing through CG, normal reaction passing through CG? It's not appropriate. Try to take this example. That means I'm applying a force on this body, right, which is less than that of the limiting friction. But due to this, there will be some friction force acting, and this friction is trying to rotate this body, or it is creating a movement about point G. Is that actually happening in this scenario? Technically, if I say the body is in static equilibrium, so all these conditions, that is the total summation of force and total summation of movement, should be equal to 0, and that is not at all happening in this situation. That means our approach is wrong. That means there is some concept clarity that we need to have, because according to this particular understanding, this body should not be in equilibrium, because this force is creating a clockwise movement about point G. Okay, now let us rewind. Let us rewind our discussion one more time. Let us suppose I'm having a block. I'm having a block on which an external force P is being applied. Okay, if I try to analyze this particular segment in an enlarged surface, so we'll be having multiple point contacts, right? So, and we know that the normal reaction will always be acting normal to the surface, right? It will be at different angles, right? Let's say this is N1, N2, N3, N4, so on. So if I try to resolve, we'll be having one frictional force F1 and the your R1 as the we can say one of the resultant, right? If I try to resolve, we'll be having the friction force, right? Friction force and the we can say the net resultant force. Okay, fine. Now, if I try to visualize at each and every point, the normal reaction is having different angles. But yes, okay, if we're talking about a static equilibrium, it will always, the net force acting should always be equal to the total weight. But due to this application of the force, what has happened is, if I again redraw the FBD, right? This is your center of gravity. This is the center of gravity at the center. The weight will still pass through this point W, but now the normal reaction has been shifted towards the force, something over here. Okay, this is the friction force, and normal reaction, the net normal reaction will be acting towards, because if I try to take the same example, okay, if I try to take at different points, the normal reaction will be acting in a linearly increasing way. This is the force. So N1, N2, N3, N4, N5. If I try to take the entire summation, the normal reaction will be having slight amount of offset from the CG point. Okay, from the CG point, it will be having slight amount of offset. So if I say this point is X, now if I try to understand, okay, let us say this point of contact, is basically, let's say Q. Okay, where this normal reaction is acting, let us say this point is Q. Okay, so if I try to calculate the total horizontal force, what will be the total horizontal force? Total horizontal force will be equal to 0, because P and F will be equal. Total vertical force will be equal to 0, because your weight and N will be equal. Now, if I try to calculate movement about point G, what will be that? We'll be having your W into X in the anti-clockwise direction. Let's say this is, I'm acting at an H by 2. I'm acting a force at point H by 2. Okay, fine, right? So W into X by 2 minus P into H by 2. Okay, and that is equal to 0. Now we are having a condition that the moment is also equal to 0. So now we have understood that whenever on a body, if you're applying a force, if you're pulling or pushing, neither any one of the cases, if you're applying a force and if that body is in static equilibrium, the normal reaction will be shifted from this CG point. The normal reaction will be shifted from its CG point. Okay, is this clear? Right? The normal reaction will be shifting from the sim. Now, again, the question is, sir, where is that concept of tipping they are talking about? Still not, we are reaching to that point. Okay. Now, let us suppose, if I try to resolve this, we can say W into X is equal to the applied force into H by 2. Now, we know that total horizontal force is your P is equal to F, right? And the total vertical force equal to 0. That means your W is equal to N. What is F? That is mu into N. F is equal to mu into N, right? Okay. So let us suppose if I apply this P value, P is equal to Wx2 by H. Okay, Wx2 by H. Now what is happening is, if I'm trying to increase the force, if I try to increase this force P, if the force P increases, right, then the distance with the X also increases in order to have that static equilibrium, because if this p increases, if this p value increases, this x value also be increasing, because I need to keep this particular relation to be at equilibrium. Okay, if you're increasing the level of p from the CG, if it is moving, let us suppose you're applying a force p over here, it will create a clockwise movement. This your a normal reaction, okay, or we can say this weight will be creating, this weight will be creating an anti-clockwise, so it will be always countering out with each other. So this normal reaction will be shifting according to the application of the force. This, if the p value is increasing, the x value is also increasing, right? If I'm increasing this magnitude of p, then what will happen? If you increase the magnitude of p, this x has to increase. Okay, fine. Let us suppose if I increase the value of h, if I increase the value of h, I have to decrease the value of p, right? Then only this will be, if I try to apply a force above the CG, if I apply a force P above the CG, right? So definitely I have to decrease the magnitude of the force. If I'm increasing the magnitude, there's a chances of toppling. Okay, fine. There's a chances of toppling. Very important point. Or I can say x is equal to p into h by 2 into w. Okay, we can simply understand like this. If I try to increase the value of p, x increases. If I try to increase the value of h, your x value also increases. If you try to decrease the value of the body, the x value increases. Okay, fine, right? So my question is, initially when the body was at rest, okay, no problem, the total reaction force was passing to the center of gravity. When we are applying some force on the body, the normal reaction has been shifting from its CG point at a distance x. So can we say, if I try to increase the application of the force, this distance x will be increasing. So can we say what will be the limiting condition? So limiting condition will be, we are increasing this value of this force, the p value, such a way that we have reached this particular point, that end point, and that point we call it as tipping. Because if I try to apply that much amount of force, I'm applying that much amount of force, which is basically making that normal reaction to be shifting about its corner point. Okay, because the more you're applying the force, the more the this normal reaction will be shifting towards the direction of the force. Okay, fine. So this is the frictional force, this is the CG, this is your weight W, right? So if I want the body to topple, for tipping condition, for tipping of body, for tipping of body, can we say that the moment about point, let's say this point is G, let us suppose this, or this point is Q. So can we say the moment of this point Q due to point P, okay, due to the moment about Q due to P should be greater than the moment at point W due to weight. Yes. If I say, if a body is about to tip, that simply means that the moment being created by this applied force should be more than that of the moment being created by the weight. Or can we say that, let us suppose this height is h, right? So P into h should be greater than that of W into, let's say this is your width B, so this will be B by 2, right? Or I can say this h is basically should be greater than W into B by 2P, right? Now I'm talking about limiting condition. So definitely can we say that this friction will be equal to the limiting friction, that is equal to your mu into n. This friction will be simply the limiting friction, because at that point only the body will be having the limiting case. So F is equal to mu into n, W is equal to n. So can we say F is equal to mu into W, right? Okay, so we can place this value of and P is equal to F. Okay, so placing entire values over here, so W into P by 2, P can be written as F, that is mu into W. So H is basically, we are getting the value, very important, H should always be more than that of B by 2 mu. B by 2 mu. That means if you are having a block which is having a thickness of B, right? Okay, and if you're applying a force more than that of this height, If you're applying a force more than that of this height, then body will be tipping about this. The body will about to tip. So can we say if this h height is less than, or let me write the limiting case. Now can we say that for body to about, or we can say for tipping, right, the height of this force being applied from the base should be always be more than that of this particular height. Okay, so for tipping condition, this particular condition must be satisfied. Or I can say that, very important, now we are coming to a very conclusive statements, right? Or I can say if if h is less than, if your h is less than b by 2 mu, then what will happen? That means your height is not that sufficient. The height of this particular, let us say this is that same block, this is that width, okay, this is the height about which the force p is acting. So this height is not sufficient enough. So in this case, the body will always have only sliding motion. The body will always have only sliding motion. You can do this experiment at your home also. Let us suppose this is a body. If I try to apply a force at the bottom, it will always have a sliding. But as soon as we are increasing that height, if I try to apply the same force, there will be a condition that the body is tipping about its one of the edge. Okay. If I say if the height is exactly equal to b by 2 mu, that means it is on the verge of tipping. On the verge of tipping. Okay, right? And if your h is greater than b by 2 mu, then we'll be having only tipping motion. Only tipping motion. Is this clear? The body will always have only tipping motion. Now tell me one thing, very interesting fact. If your friction, there is no friction, that means if your mu is tending to 0, that means we're having frictionless surface. Frictionless surface. So if you're having a frictionless surface, then what will happen? If you're having a frictionless surface, then what will happen? Your h will be tending to infinity. That means the force should be applied at a height which is equivalent to infinity, which is not possible. That means in this case, what will happen will be always only sliding motion will be happening. Only sliding motion. Only sliding motion will be coming into existence. Is this clear? Right, very basic, very very easy. So if and that is the reason when you try to push an almirah which is full of clothes, we always try to apply a force near about to the midpoint or below the midpoint. Okay, if this is the height, we always try to, if I say this is your center of gravity, so we always try to apply near about the center of gravity. We never ever push that almirah above the center of gravity, because if you try to push, there are chances that you are applying a force. Which is at a height which is more than that of b by 2 mu. And if this is happening, the body will tip. The body will topple, or body will tip about its corner point. Okay, so this is the entire. Now, one more doubt you will be having, sir, then why when we are drawing the free body diagram of the bodies, we are always taking the normal reaction from the CG? Why we are not taking the offset? The reason being, the bodies which we are dealing with in our competitive examinations, we are only talking about smaller bodies. So their x is very tending to, we can say, very small value. So there we can say approximately the normal reaction is passing through G. Okay, so there we can use this free body diagram, because we won't be having that problem, because this x is very small, so we won't be having that much of difference. But yes, if we're having a body whose height and width is being given, that means we have to take this as a standard free body diagram, not this one. Okay, so this is all about the condition of tipping. I hope so you all enjoyed. Please feel free to write in the comment section if you liked, and if you want more such awesome content, stay connected. We are on very best preparation learning platform, that is BYJU'S Exam Prep. Thank you guys. Stay safe, stay connected. Thank you. Bye bye.